Now we're going to section 5.3, and this is one-step proofs or just one-step justifications. We did these in chapter 3. We're just going to add some more things to it, like the idea of congruence, etc. So here we have a problem where we have a circle, and our conclusion is that AC is equal to AR, or in other words, the length of AC, the distance from A to C, is the same as the distance from A to R, and this would be justified by the definition of a circle. This is another one. It's saying the picture, the given is the picture. We conclude that the measure of angle 1 equals the measure of angle 3. That is, of course, the one we've done before, and the vertical angles theorem justifies that. Now, this is one that came from the earlier in chapter 5, rather. If we know that ST is equal to HK, again, remember this is saying the length of the two segments are equal. The lengths are equal. Then we can say that the segments are congruent. That is where we use the segment congruence theorem. So here we're going to do one-step proofs, or one-step congruence proofs. We're going to both make and justify conclusions about congruent figures. Some of the common justifications we're going to run into. Definition of perpendicular bisector, definition of midpoint, the CPCF theorem, segment congruence theorem, definition of circle, and definition of congruence. Remember, you're going to need to know some of these specifically, like definition of congruence. We have to have an isometry. Hopefully you'll figure that out as we go. Definition of midpoint we did again back in chapter 3. If we know M is a midpoint, we can conclude that AM is equal to MB, or we can conclude that segment AM is congruent to segment MB. If you say segment, if you put the segment symbol above it, you should have congruence with it. The CPCF, we have to have the congruent figures. So for instance, given might be that triangle ABC is congruent to triangle XYZ. If that's the case, then we can conclude that the individual pieces, the angles or the segments, are congruent or equal. So we could say equal, or sometimes we will say that segment AB is congruent to segment XY. Segment congruence theorem again, if we know they're equal, we can then conclude that they are congruent. Definition of circle, if we know they have a circle, then we can say that those AC is equal to BC. C is the center of the circle. Sometimes we could also say that they're congruent. A lot of times that segment congruence theorem, you won't always use that. Definition of congruence, if we have a reflection, we have to have an isometry. In this case, it's a reflection. So if the segment, let me put the segment symbols on there. If the segment QR reflects to JK, then we can say that segment QR is congruent to segment JK. That's where we use the definition of congruence. We have to have the reflection. Common angle justifications. Remember the corresponding angles postulate, angle bisector, CPCF, vertical angles, etc. Some of these again are the same as the ones we did with the segments. The corresponding angles postulate, of course, we have to have the parallel lines. We would have to have, that picture with A parallel to B. then we can conclude that angle 1 is congruent to angle 2 by that corresponding angles postulate. Definition of angle bisector, we could go in both directions, but generally we have an angle bisector. Maybe let's write it this way. Ray AB bisects angle CAR. So here's our angle CAR. There's AB. If it bisects it, then we can conclude that angle CAB is congruent to angle BAR. CPCF again, corresponding parts of congruent figures. Angle congruence theorem, if I know angle A is congruent to angle B, that's a given, then I can conclude that the measure of angle A is equal to the measure of angle B. Vertical angles, of course, done that before. Definition of congruence, again, we'd have to have a reflection or some isometry to match up. And that does it for that set. Hopefully that will help you get through section 3.